Okay, we're back to talk about Earth's internal structure and some other details about boundaries. So there are three main zones, very similar to the sun discussion. The crust is the outer thin shell. Then we have the mantle, which is much thicker than the crust, and then the core, which is actually broken into inner and outer core, which is the centralmost part of our Earth. So the crust is going to cover the entire Earth. We have two different types of crust, as I said before. The oceanic crust is going to be the crust that's below the ocean water. It's very much thinner. It's made out of basaltic rock, making it more dense, which is heavier. The continental crust is going to be predominantly granite rock, which is less dense. And then there is this mantle crust boundary, which is called the mohorific discontinuity, which is often called just the Moho discontinuity. And this is where the seismic wave velocity will increase sharply from crust to mantle just because the differences in the materials that the crust and the mantle are made out of. The mantle is the next layer. It's the thick shell between the crust and the core. It makes up 80% of Earth's volume and accounts for 2/3 of Earth's mass. So it's significantly larger and heavier. It's composed mainly of olivine, which is a ferromagnesian silicate, which makes it magnetic in nature. And we have three data sources to tell us about our mantle, because we can't drill there to get there, which is seismological data, the nature of meteorites, and materials that are ejected by volcanoes, because that's coming from the upper part of the mantle. The basalt correlation is that because it's the most common volcanic rock and it's similar to the composition of stony meteorites, tells us some stuff about our mantle that we wouldn't know otherwise. Now, the seismic waves are going to help us to understand Earth's interior. We're going to talk about two different types of waves, the P waves and the S waves. P waves are longitudinal, compressional. Think about our waves we talked about with the slinky before. They travel the fastest and they can move through surface rocks interior that are solid and liquid, so that's important. The S wave is a shear wave or transverse, second fastest wave, and they do not travel through liquids, will only travel through solid materials. So the core, we can't get to the core. If we cannot go to the mantle, we're definitely not getting to the core. It makes up 15% of Earth's volume, so essentially the crust is next to nothing, and about 1/3 of Earth's mass. Again, the crust is next to nothing. So P wave seismological data is very useful because what we see is if we have a source of origin for P waves, and then we try to detect them on the other side of the Earth, we see that the P waves are detected all of here, here, and here. There's only this small shadow zone where we don't detect waves. So we use this to calculate the shape and the size of the core. And so it gives us source of data on the interior makeup of the core, which tells us there's probably going to be, if we think about it, about P waves, it could either be solid or liquid. It isn't until we look at the S waves that we start to understand whether it's solid or liquid. So S wave seismic data tells us that there's a larger, if we have the same point of origin, these S waves are going to hit the core and essentially be blocked out where there's no S wave detected once it travels to the core. So what this tells us is that the core acts like a liquid because it doesn't allow S waves to pass through. What this tells us is the core is most likely made out of two parts. There is a liquid outer core, which is acting like a shell, a shield for the S waves, and there's a solid inner core, which is supported by both the S wave and the P wave data that we discussed. Other core evidence we have are iron meteorites. They're made of mostly iron and iron nickel alloy, which we think mimics the chemical composition of our core. We know that Earth has a magnetic field, which is consistent with having the iron nickel composition, but we also know that our core must be a source of turbulent flow within the liquid core. It couldn't just be a magnetic rock. The material must be able to conduct electricity. Meteorite and magnetic field data is consistent with an iron core. Now, a more detailed structure of the Earth would include two additional layers we didn't discuss, which is the asthenosphere and the lithosphere. And these are important when we start talking about plate tectonics, which we're getting there. So the asthenosphere is going to be a thin, hot, elastic, semi-liquid layer in the upper mantle. So these are located in the mantle. The lithosphere is a solid layer above the asthenosphere, which includes the crust, the moho, and the upper mantle. So it's the upper part of the mantle, all through the discontinuity, and the crust. And these are our plates. They are made up of rigid plates floating in the upper mantle. So essentially, if we look at here, the lithosphere is all three of these combined. The asthenosphere is part of the mantle, but it's liquid. And so these plates can float around, and as you might guess, can cause earthquakes, which we're going to talk about, though not today so much. So theory of plate tectonics is going to be the second half of this day of lecture. So go ahead, take a break, and then come back and finish up this chapter 15.